Okay. Can you see my screen?
Yes, doctor.
So what do you see?
Wood.
Yeah, it's a blank document in the Microsoft Word. So basically, in this case, what I want to share to revisit is the overall guideline for dynamic model. This is just to revisit what has been learned so far in our class. So based on this, normally we start with the step 1. Step 1 is based on the process understanding. So this guideline is applicable to any kind of the chemical problem for relating to the process control, where first step involve the process understanding. In the process understanding, we take a look on what unit operation involved, what kind of process, unit operation in, out from the system, and the certain assumption. So this means before we are going to solve our model or we proceed with the derivation, we need to understand regarding the process involved. So what is the purpose of the process? For example, is it for the blending system, for the reacting system, and so on. So for this part, normally we want to see, based on the process, what is the necessary balance that needs to be developed. Sometimes for the blending system, it's just maybe the composition, and in the storage tank, it's just a level. So not that we don't need to derive all of the balance. Only selected balance is required to solve the model, because we need to respect or we need to obey the time given. For example, in the test, 1 hour is located to solve the model. So it made no sense to derive all of the mathematical model, which may consist of the level, composition, or the energy. At most, there will be two balance, either the overall plus the component or the overall plus the energy. We don't ask you to derive all of these three balance. That's why in this case, the assumption is very important. So you need to take a look which variable is constant. For example, in some cases, the process is under isothermal condition. So when you operate under isothermal, there will be no change on the temperature. So you don't need to develop the energy balance. So this process understanding will definitely shaping your required balance. So once you understand based on the process understanding, the step number 2 is to derive the required balance. So the required balance, this one may consist of the overall, component, or energy balance. So here, how to know which balance that required to be derived is based on the assumption and the process understanding. And then number 3, for the step, we require the deviation variable. So once you obtain the derivation, then you need to develop the deviation form. So dynamic state minus the steady state condition. And then once derivation 4, it will go to the Laplace transform, where you convert the ODE into the Laplace transform, which is based on the S. And then here you get the Laplace transform. You will develop the what we call it transfer function. Where in the transfer function, the definition is based on the output over input. Output over input. And the transfer function normally has the symbol of the G, capital letter of G, S. So the GS represent the output over input, the variable of the output divided by the input variable. So based on the transfer function, normally we will form what we call it first order. First order transfer function. So where the standard form for the first order is GS equal to K over tau S plus 1. Where here this is the standard. If you refer to the textbook, for example, the third edition. Third edition, page 61. So this is the standard form for the first order, GS equal to K over tau S plus 1, where you can find there are two parameters. The first one is the K. This K is called as the process gain. And the tau here is the time constant. Then you have the S. S is the Laplace, plus 1 is the standard form for the first order transfer function. So why we need to obtain the transfer function in the form of the first order? So remember that in this case, we already do the Laplace transform. And then we obtain the transfer function, and the next step related to the inverse Laplace. Where we convert back the equation in the S function into the time function. So when we have the first order transfer function, then it's much more easier for us to obtain the inverse Laplace in the form of the time. Where if you get the first order K over tau S plus 1, when we assume the step based on the step input, let's say step input with the magnitude M, then your inverse Laplace in the time domain become the YT equal to Km 1 minus exponent negative T over tau. So this is the standard form of the inverse Laplace for the first order. So this is the thing that you need to understand. Because here right now we want to obtain. Originally your equation, for example, the overall or the component is in the dH over dt, dx over dt, or dt over dt, based on the differential equation. So we want to solve this problem. So one of the approach that we can solve is by using Laplace. So for the Laplace transform, the first step involving conversion of the ODE inside into the S Laplace. So once you get the S, then we can obtain the transfer function based on the output over input variable. So for the first order, the requirement is to have the plus 1 for your equation. And then based on this, you have two additional parameter, which is called as the process gain and the time constant. The process gain located at the numerator, the tau be located at the time constant. So when we obtain the first order, then automatically we can employ the time domain expression. This is the thing why you need to convert in the form of the first order. So normally, for example, you have equation like this. You get 4 over s plus 2. So for this form, normally you cannot use the yt-km 1 minus exponent negative t over tau. So for this part, since the denominator you have the plus 2, so we cannot use the straightforward inverse Laplace. So another form of the Laplace is required to inverse the Laplace. So for this part, normally when you have the plus 2 over here, you need to make sure it become plus 1. So this part must become plus 1. So in order to do that, so you can divide it 4 over 2, s over 2 plus 2 over 2. So where this one become the 2 over 0.5 s plus 1. So once you obtain like this, then straight away you can substitute the parameter inside the given time domain response. So this is the advantage, the usefulness of the first order transfer function. Based on this, let's take a look on one example. Go for the Excel. Okay. Can you see my Excel file?
Yes, sir.
All right. Thank you for your response. So let's say we have the GS equal to 2 over 5s plus 1. And then let's say my step input equal to 3. So when I want to plot the dynamic response, it will come like this. So our response will be yt equal to k m 1 minus exponent negative t over tau, where k in this case k equal to 2, m equal to 3, and tau equal to 5. So we just substitute the value to obtain the y value. So let's say here the t represent your time and the y become my output. So here let's say I put 0 equal to km 2 multiplied by 3 by m, magnitude is equal to 3 multiplied by 1 minus exponent negative t over tau. Tau is 5. So at T0 y equal to 0, so it's okay. So let's say here I put 1, 2, 3, 4, 5. Then we can see the response is changing. So if I try to do the plotting, so here you can see this is the kind of the graph that you will be obtained based on the current profile, where based on the transfer function 2 over 5s plus 1, the step input is 3. Step inputs mean the input that I use, the magnitude that I use for our case is 3. Just for illustration, you can use any kind of the value for this case. What I want to show here, normally the first order, if you take a look, the first order response will be increased when you have the magnitude, positive magnitude. Then your response will be increased. And when it is increased, you can see it's increased from the 0 and then it slowly reach the 6 value. The 6 value here represent the final value. If I try to increase the time, for example, here I put 200. You still get 6. I put 1000. You still get 6. So meaning that it's not going to change anymore. Although you increase the time, still you get the same value. This means the process has reached new steady state. So this is what we call it new steady state value. Initial value will be 0 and the new steady state value is equal to 6. And this is the thing that the characteristic of the first order. When you have the positive magnitude, the response will steadily increase and reach new steady state value. And let's say, in this case, we have the positive magnitude. How about if we have the negative magnitude? So I just change here. Let's say here I put -3 as my magnitude. So I will get the different profile. All right. So based on this, if I try to focus it, you can see in this one clearly. The magnitude in this case influence either the process or the graph will be increased or decreased. Based on the figure below, you can see the graph is decreased. So the decrement or the increment depending on your magnitude. If your magnitude is positive, then your response will be increased. If your magnitude is decreased, then you will have a decrement trend. So this one is based on the negative magnitude. So in this case, what we can see is the magnitude influence, either your process is increased or decreased. So since we have the K over tau S plus 1, in this case, you have two coefficient, which is two parameter, which are the process gain and the time constant. So for this part, normally the process gain should be in the positive value. K, if negative, then then it will become a problem to your process. So it's preferably to have a positive value. The same goes with the time constant. Time constant cannot be negative because it represents the time. Time will be increased. For example, now it's 12:25. It will not go back 12:20, 12:20. You will go further, 12:26. So that means the trajectory for the time will be increment. So you will have the positive value only. So normally in this case, if the K is too high, then the final value will become increased. The K here influence the final value. For example, in this case, your K is 2. K equal to 2. Then 2 multiplied by 3, you get 6. That's why your new steady state becomes 6. If let's say your K equal to 3, then 3 multiplied by 3, you get 9. So the final steady state value become 9. So when your K is increased, final value will be increased. So this is the characteristic of your K. And then the tau. What happens if I use smaller tau or highest tau? So in this case, we can see. So let's say in this case, I put Y1. And then this one is for this part, instead of using 5, I use, let's say 10. Double the tau value to see what happened. Alright. So in this case, you can see there are two types of graph. The first one is the blue one. The blue one here represent tau equal to 5. And the orange one is the tau equal to 10. So when I increase the tau value, what happened to our response? It's become slower. Tau increase, response becomes slower. So when the response becomes slower, means that if you can see, compared to the tau equal to 5, the response in the orange color reacting slowly, in the slower rate, compared to the blue one. Blue one reach the final value around this point. But for when the tau is increased double from 5 to 10, it reach around here. So this is what we call it slower response when you increase the tau or time constant value. In this case, the tau is increased from 5 to 10. So this is the characteristic of the first order. Any question?
Sir, if the K is negative, the graph will be like below there, isn't it? Like it shows the decrement, isn't it?
In this case, the K cannot be negative. K must be positive, the tau must be positive. Only the magnitude can be negative or positive.
What does mean the magnitude, sir? I don't really understand. I mean, what causes the YT to be negative?
YT to be negative. Alright, so in this case, normally we have the input when we want to develop the transfer function, it become output over input. So here, let's say the output will be the YS, the input will be the US. So Y output, U input. And then here, let's say we have the first order. K tau S plus 1. So in this case, we have the output. This is our output. And this is our input. Now, how the input can be negative? Because here US is represent your step input. So this is example of the step input, where you can see the input has been increased from one point to another point. The change, we call it magnitude M. Or the input can be decreased like this. So both is you have the different kind of the value. When you increase, it become positive. When you decrease, it become negative M. So US, when we have the M or negative M over S, represent the increment or decrement. So this influence why your graph is decreasing or increasing. Notice that the K and the tau cannot be negative. It must be positive. Only the magnitude can be positive or negative. Here the input normally is the one that we will specify. For example, in our cases, certain cases, the input should be our flow rate. So the flow rate either be increased or being decreased. So it's like that. So let's take a look on one example how to demonstrate it. We refer to our tutorial before. All right. So let's recall this tutorial. This tutorial involves the tank with the pump and the tank with the valve. So based on this, we have the first order, where our first order here is -2. -2 over 0.5 S multiply with the 7.0685 s over 0.5 plus 1. Where in this case, we have the km equal to -4 and the tau is 14.14. So how come the km is negative? Because of the magnitude. If we read it, we read the equation again, you can see the inlet flow rate suddenly changed from 7 to 5. So this represents the input flow rate, input change from 7 to 5. So the magnitude is 5 minus 7. 5 minus 7 equal to -2. So this is where the magnitude coming from. So according to this, we get the tau equal to 14.14. And then based on this, h minus h bar equal to -4. So let me copy this one. So the last time when we try to solve it, some of you get the math errors as a solution. So today we are going to see why you get math error. So in this case, there's one more thing. What is our h bar? H bar is 14. All right. H bar 14 and then this one. Okay, this is our equation that needs to be solved. So in this case, h minus h bar. H minus h bar. And then this is my t. Okay. So I put t equal to 0. H minus h bar equal to -4. Multiply with the 1 minus exponent. Negative t over 14.14. Alright. And then this one is my h. So h equal to 14 plus. 14 plus this one. Alright, so I put 5. And 10, 15, 20. Alright. Okay, in this case, this is my profile, level profile. Level profile. And then let me include the design a little bit. It's my time. And this is my level. Okay, so based on this, just to recap, just to get the overview, this is, I refer to the previous exercise, the one that the tank with the pump and the tank with the valve. Based on my solution previously, that is indicate that based on the case 1 using pump, it took around 50 minutes for the level to reach 0. 14 to 0 is just around 49.49. Now for the case 2 valve, when I try to solve it, alright. Based on the current one, I get the first order. So I use the inverse Laplace of the first order to determine to obtain the time domain response. Based on my solution, it shows that this is my level profile. What do you see? What do you observe from this graph? Muhammad Amir? Muhammad Amir?
Muhammad or Amir?
Bukan Amir Syarifuddin, Muhammad Amir. Mana Muhammad Amir? Mana hilang. Ahmad Akif? Ahmad Akif.
Yes, Doctor.
Okay. What do you see from this graph?
From the 600 from the time of 600 until the end, the level is hampir sama, Doctor.
At 10, right?
Yeah.
So this means in this case, the level initially at 14. And
Yeah.
then it will reach new steady state at 10.
Yes.
So back to the question, when it will reach 0? When the level will reach 0 height. That means it become empty.
It will never reach empty.
Yeah, betul.
It's never reach empty. If let's say in this case, you can see from my data, I put 3010. Okay, so now I put 10,000. What happened? Still I get 10. And then I put almost 1 million. Still I get 10. So that means if I try to increase the time, still you're not going to change the steady state value, which is 10. So for this part, that's why if you try to recalculate it to find the time, based on this, you get t equal to met error. Because you never going to reach that value. So when we try to solve mathematically why it become met error, then we need to find what is the consequence or what is the factor contributing to this map error. So we track back. We do the calculation, we put the value of the time, and then we found out that the response is going to decrease, but it's just decrease until 10 feet. It will never going below that. So this indicate that the tank, when based on the current situation, based on the current condition, is never going to be empty. So this is the answer for this question, where here the question asks you to predict which tank will empty first after a long period of operation. So this means when I try to increase the time, the tank with the valve will never become empty.
Doctor.
Yeah.
So means that if we calculate mass error, do we need to like prove like doctor draw the graph out, or we just that you claim that it will never empty, then it's enough?
It's if in this case it's better you prove it.
Okay, understood. Thank you,
You
doctor.
prove it, you put one value to indicate, okay, when I put 1000, you get 10 feet. So it's never going to reach. Don't simply put math error. So if you put the math error, that means there is no justification on that. So why math error? You put the justification. It's never, when you put the time equal to big value, the steady state value is not going to change. Just contribute to the math error. Any question relating to the first order?
Doctor, would you mind to
Yeah.
let me see your Excel equations that you key into the H minus H bar for the first
This one?
H minus H bar.
Uh-huh.
Because I'm getting another answer. I'm getting like, yeah, wait. For the negative 0.1 something.
At time equal to?
Yeah, this one correctly. B12. Okay. Okay, thank you, doctor.
If I make a mistake, just point out so I can rectify the mistake. I'm not saying I am the perfect one. No problem on that. All right. So here, any other question? So that's mean for this part, why your graph is decreased because your magnitude. So the magnitude is
Doctor,
show, yeah.
I think that you made a mistake for the 14-14. It's actually 14.14.
Oh, this one. Okay, sorry.
Yeah, it's an increasing graph.
I correct it. Okay. Is it what you get?
Yep, doctor.
Okay. Only here still the same. It's until 10 feet. Only is much more steep response. But the answer will be still similar. It will never going to reach the empty condition. So any further question relating to this? All right. If there is no further question, then we proceed with the discussion on the second exercise, which is this one. So here a steel tank heating shown in the figure 1 is used to preheat a reactant containing a suspended solid catalyst at a constant flow rate. So like I mentioned before, when we go through the guideline, you need to have the process understanding. So for this part, the unit operation involved is the steel tank heating. So when you have a steel tank heating, of course, it will involve the preheat reactant. When you have the preheat, that means the temperature is going to change. And then, based on the statement, preheat a reactant containing a suspended solid catalyst at a constant flow rate. Constant flow rate of 500 kg per hour. So the use of the flow rate is in the form of the mass. So you have the mass flow rate. So in this case, based on the diagram at the figure 1, you have one inlet and one outlet. So meaning that you have the constant flow rate. So W in equal to W out, automatically equal to 500 kg. Mass in equal to mass out. The volume in the tank is 4. V equal to 4. The density, given the density is 1050. And then the specific heat, Cp, equal to 5. So this is the operating condition, the volume 4, flow rate fixed at 500, density 1050, and the heat capacity equal to 5. And the last sentence mentioned about the process condition. The process initially operating with inlet and outlet temperature of 150 and 200 degrees C. So the term is initially. Initially means the process at the time 0. Time 0 means the value of the Ti bar. Ti at the steady state value. Ti at the steady state is 150 degrees C. And then the T outlet, T bar, equal to 200 degrees C. So this is the condition. A. Develop differential equation describing the dynamic behavior. Alright. So in this case, we know that when we try to do the overall mass balance, you don't need to show the derivation because it's just mentioned the constant flow rate. And then you have only one inlet and one outlet. So automatically the W in equal to W out, which is 500 kg per hour. So you don't need to do the derivation. So the one that matters is the energy balance. So in the energy balance, in this case, we start as normally as in the dE over dt equal to E in minus E out. And then we take a look. In this case, you have the heater. And then you have the Q. So this means there are heat added into the system. So you have plus Q. So E equal to U KE plus PE, where KE equal to PE equal to 0, neglected. because we assume the tank will be stationary and not moving, so E equal to U. So this become du over dt equal to E in minus E out plus Q. So the U here, we can expand it equal to H, the enthalpy, where we assume there is no pressure change. So U equal to H equal to mH or mCp delta T, where mCp delta T equal to mCp T minus T reference, where T reference equal to 0 for simplification. So when you have the T reference equal to 0, then your equation become U M Cp T. Or in this case, you can further expand the M with the density multiplied by volume. So you get rho V Cp T. So this expression then can be substituted into your equation. So you get the d rho V Cp T over dt equal to E in based on this one, W in Cp in T in minus W Cp T. So this will be based on your diagram. So this one Ti Wi, this one Tw. So we have W in, Cp in, T in. If you are not sure, one of the way is to trace back using the units. For example, W here is the kilogram per hour. Cp, kilojoule, kilogram, Kelvin. T, let's say in this case, Kelvin. So when you try to cancel, you get kilojoule per hour, which is the unit of the energy. That's how you can confirm your value of correct or not. Plus the Q. So based on this, we have the left hand side of our equation. You have d rho v Cp over T, d rho v Cp T over dt, where the density, volume, the density we can volume, the Cp are all constant value. So when all are constant value, then you can take it out. So the equation can become rho v Cp dt over dt. Equal to W in Cp in T in minus W Cp T plus Q. So based on this, we can do the derivation form, where your equation for derivation form this one is based on the dynamic state. And then for the steady state, rho V Cp dt bar over dt equal to, so the W in is constant. Mass flow rate is constant. Cp is also constant. Only the T in will be changed. So you put the bar minus W Cp T bar plus the Q bar. So this represent the steady state equation. So in the end, when we try to develop the derivation form, it become rho V Cp dt prime over dt equal to W in Cp in T in prime minus W Cp T prime plus Q prime. So this is your equation for the derivation form, where T prime equal to T minus T bar, T in prime equal to T in minus T in bar, and then the Q prime equal to Q minus Q bar. Okay, so this is your derivation form. So in this case, the question asks you to develop differential equation describing the dynamic behavior. So this is the equation for A. Any question?
Doktor, tadi doktor
Ya.
cakap, we no need to do the derivation because of Lorentz constant. Lagi satu apa?
Lagi satu apa?
Tadi apa?
Okay, in this case, here the question asks you to develop differential equation describing dynamic behavior. For this part, normally for the overall mass balance, you don't need to do the complete derivation because it has been stated the constant flow rate. Since you involve the only one inlet, one outlet, then you simply can write like this.
Okay, doktor.
And of course, for the energy balance, you need to show the detail how you derive, because this one is the only matters, the balance that matters. And then for this part also, if we take a look, there are three balance that needs to be developed: the overall mass, the component, the energy. For this part, component balance is not required. Why is not required? If you take a look, there is no mass fraction, no concentration given. So, and then the main objective is to preheat a reactant, just to preheat. So this means the component change will not be relevant. So don't waste your time deriving unnecessary balance. So any other question?
Doctor, may I ask about why the Q is necessary to Q pi in the end of the equation?
Why we have the Q prime? Okay. So in this case, if we refer back to the picture, we have the Q heater. So this is your heater. Where the Q in this case represent the heat adding into the system. And normally when we try to add the heat into the system, it will influence the temperature. So let's say your temperature is too high, maybe you need to decrease the amount of the heat. If your temperature is too low, then maybe you need to add more heat. So that means this amount we keep adjusting. When it is keep adjusting, that means it will never fix. you have the initial value and the value will be changed at the next time. So that's why in this case you have the Q prime, because the amount of the Q will keep changing depending on the value of your temperature.
Okay, thank you, Doctor.
Alright, so we move to the next question. So this is your next question. Suppose that the inlet liquid temperature, so the question B, suppose that the inlet liquid temperature was decreased from 150 to 100 degrees C. So here the inlet liquid temperature is T in. T in was decreased from 150 to 100 degrees C. So remember that initially, this is initially inlet temperature is 150. Now it has been changed to 100. So here we just use T in bar equal to T in minus T in bar. T in prime equal to T in minus T in bar, as has been developed for this part. So when we try to do the derivation form, we get the T in prime equal to T in minus T in bar. And then in this case, the T in prime equal to T in is 100 minus 150. Why we put the T in as 100, T in bar is 150? Because initially the inlet liquid temperature specified is 150 degrees C. So it has been changed to 100. So here the T in minus T in bar is based on the final value minus the initial value. So you in here T in prime equal to negative 50. And then the second sentence, determine the heat duty required so that the outlet temperature is maintained at initial steady state. Outlet temperature is maintained. So when we have the T outlet, T prime equal to T minus T bar. So the T bar for this case given is 200. T bar is equal to 200 degrees C. So the question asks you to maintain the outlet temperature at initial steady state. So we know that T bar is 200. It maintained must be 200. So T prime in this case must be equal to 0. Because the value has been maintained for outlet temperature. So now the condition want to find when your inlet liquid temperature decrease, outlet temperature maintain, what happened to your heat duty? This is what the question want you to solve it. So we will use the derivation form equation. So this is our equation. So based on this, we will use the derivation form rho VCP dt prime over dt rho VCP dt prime over dt equal to W in Cp in plus Q prime. So based on this, we know that the T prime equal to 0. When your T prime equal to 0,
Doctor,
Yeah.
we can't see your writing.
You can see my writing. Macam mana saya nak tahu? Alright.
Tak ada apa Doctor, dah nampak ya. Saya sebab saya ni kot. Saya yang spike.
Sekejap, saya try to unshare balik. Okay, nampak tak?
Nampak Doctor.
Okay, alright. Sebab saya pun tak tahu apa yang you nampak kan. So if in the case you don't see any kind of the thing, please mention it to me. So based on this, we use the deviation form to find the heat duty required. So the deviation form is the rho VCP dt prime over dt equal to W in Cp in T in prime minus WCP T prime plus Q prime. Alright. So in this case, for example, let's say here the W in is equal to W equal to 500. The Cp in also we can assume it's similar with the Cp. So the Cp in this case 5. Cp is 5. So this equation can be factorized if you, for simplification. Rho V Cp dt prime over dt equal to W Cp T in minus T prime plus Q prime. So either way, if the variable can be factorized, then you can do the simplification. Or sometimes you still can remain the equation as it is. It's up to you. There are pros and cons when we try to do simplification. First, our equation becomes simple. And sometimes when doing the simplification, we also tend to do some mistake. So this is up to you in the end. Alright, back to the question. Here we have the rho VCP dt prime over dt equal to WCP in bracket T in minus T prime plus Q prime. So based on the information given, we know that the T in prime equal to negative 50. T prime equal to 0. So we can substitute this value inside the equation. So here we know that rho VCP dt prime, T prime automatically 0. So whatever you derive, then it is automatically become 0. Equal to 500 multiplied by Cp is 5. T in prime is negative 50. Minus the T prime. T prime is 0. So we get the Q prime. So here what is the value of the Q prime?
Uh, 125,000.
125
000.
negative or positive?
Positive, sir.
Bukan negatif eh?
If buat kalau pindah Q ke sebelah akan jadi negatif. So nanti akan dapat value tu positif balik.
Okay, 125 1000. Negatif lah sini.
Positif kan kita nak tambah positif, sir.
Positif. So Q prime equal to positive 125.
Yeah.
All right. So here the question asks you to determine the heat duty required. So heat duty in this case represent the Q. So the Q prime is Q minus Q bar. So in order to find the Q, we need to find what is our Q bar. So determine the value of Q bar. So the Q bar here represent the value at the steady state. So the value of steady state represent this value. The equation for SS steady state. So you can use the rho VCP dt bar over dt equal to, so here the WCP T in bar minus T bar plus Q bar. So this represent the equation at steady state value. So for this part, normally the term in the left hand side, you have the rho VCP dt bar over dt. At time equal to 0, the time is not moving. It's fixed value. So the dt will become 0. So that means in this equation at the steady state, the left hand side will become 0. So 0 equal to WCP, W is 500, CP is 5, and the T in bar in this case 150 minus T bar is 200 plus Q bar. So the value of the Q bar,
One two five zero zero zero.
125000. So this is your value of the Q bar. Now back to the equation, we know that Q prime equal to 125000, where the Q prime is equal to Q minus Q bar. So based on this, 125,000 equal to Q minus the Q bar is 125. So the Q will be 250. Alright. So the heat required for the given system to reach Ti at 100 and the maintained T prime will be 250,000. So this is the answer for question B. Any question?
Doctor, can you explain back why fixed volume time equal to 0?
Alright. In this case, if we take a look, oops. Based on the differential variable, we construct two types of equation, where the first one will be the equation in the dynamic state. And the second one is the equation in the steady state. So the main difference in this case, we can see the ds and the ss. The ss, you have the bar, t bar, t in bar, t bar, and the q bar. So this represents the steady state equation. The difference between the steady state and the dynamic state, in the dynamic state, the time is changing. The time is moving. But for the steady state, normally the time is not moving. Steady state represents one state, which is in this case referring to the time equal to 0. So when the time is equal to 0, that means normally the first part here will become 0. Because you don't have any differential. No dt. Because you operate at the fixed dt, which is t equal to 0. So this means under steady state condition, normally the term rho VCP dt bar over dt is assumed or is considered as 0. That's why when we try to solve it, at this point we use the steady state equation. But for this part, the left hand side, the term at the left hand side, rho VCP dt bar dt, we neglect it at 0 because we operate at the fixed value. The dt, the differential of the time, is neglected for this case.
Okay, doctor.
So we complete the question A and question B. Now we can go for the question C. Determine the outlet temperature at new steady state if the inlet temperature is changed to 100 and the heat duty is changed to 300 kJ per hour. Alright, let me copy this one. Alright, so here we use the deviation form equation, which is this one or this one. The rho VCP dt prime over dt for our solution. So we have the rho VCP dt prime over dt equal to W in Cp in T in prime minus W Cp T prime plus Q prime. So like I said before, because the W is the constant mass flow rate, the Cp is also can be assumed similar. We can do factorization. So this equation become the dt prime dt equal to W Cp T in prime minus T prime plus Q prime. So based on this, once we obtain the equation in the derivation form, the next step is to do the Laplace transform. Why we want to do the Laplace transform? Because if you take a look, determine outlet temperature new steady state. So it requires us to solve at the new steady state value. That means this is require us to convert the equation into the derivation form and the Laplace transform. So we firstly start with the Laplace. So from the Laplace, it become the rho VCP S T prime S equal to WCP T in prime S minus T prime S plus Q prime S. So in this case, we can see based on the Laplace transform, we have the variable T prime. So this is our variable, the T in variable, T prime is variable, the Q is the variable. So the first thing that we can rearrange is the T, the outlet temperature on the left and the right hand side. So we can put it together on the left hand side. So it becomes the rho VCP S T prime S plus WCP T prime S equal to WCP T in prime S plus Q prime S. So we can do the factorization T prime, so it becomes T prime S rho V CP S plus WCP equal to WCP T in prime S plus Q prime S. So we already complete the rearrangement of our variable, where you can see now we have single variable on the left hand side and then two variable on the right hand side, where for the T prime we know this part is our output variable. How do we know? Because the T normally is the outlet temperature. So outlet temperature represent the outlet variable. And this one, the inlet temperature, is your input variable. Since it's inlet temperature, so inlet represent your input. The same goes with the Q. Q is your input variable in this case. So based on this, you have one output but two input. One output, two input. When normally for the transfer function, you have one output, one input. But in this case, you have one output, two inputs. When you have one output with two input, then that means you have the two transfer function. Because you have two input, that means you have two transfer function involved in this case, which is the first, maybe in the form of the, if you recall, the GS transfer function. In this case, maybe you have the T prime S over Ti prime S and T prime S with the Q prime S. So you have two transfer function involved. Here you can see the numerator is the T prime, which is your output. But in this case, you have two input, either the Ti or the Q. So this resulting into two transfer function for your case study. So let's say here we put transfer function. Based on your case, T prime equal to WCP over All right. So this is the rearrangement of your equation. Just let the t prime s stay on the left hand side because this is our output variable. So we put it on the left hand side. The rest of it, we rearrange it on the right hand side. So this indicates that we have two transfer functions, where the first one, this is the first transfer function relating to the t over ti, and the second one is the t over q. So you have the first transfer function and the second transfer function. So this is first TF. TF represent the transfer function. Second TF. So based on this, we can say that the two transfer function involved for the energy balance. And then the next step, once you obtain the transfer function, is to rearrange it or restructure it based according to the first order. First order. Where the first order must have the following form. K tau S plus 1. So here we can see that you have the S. You have the S. And then the problem is this one. Plus WCP. Plus WCP. So we need to convert it back into plus 1. So this can be rearranged. You will have WCP divided by WCP rho VCP WCP S plus 1. T in prime S plus 1 over WCP Q prime S. Alright. So here I need to convert my transfer function to represent the form of first order, where the first order is K over tau S plus 1. So now the objective is to make sure my denominator become plus 1. So that's why I have to divide WCP in order to eliminate the WCP inside the original transfer function. So when I try to divide it to make sure it become plus 1, then this is what I get. So this equation can be further simplified again, where here we can remove the WCP. This one can be removed. CP here can be removed. And then the same goes with the right hand side. CP here can be removed. So this contribute to the following form. 1 over rho V W S plus 1 T in prime S plus 1 over WCP rho V W S plus 1 Q prime S. Alright. So now, based on this, I already made sure the transfer function now has been in the form of first order. But when I try to compare it, K over tau S plus 1. And this is also K over tau S plus 1. So based on this, I can say that here the K equal to 1, the tau equal to rho V over W. And the second one, K equal to 1 over WCP. The tau equal to rho V over W. Alright. So it is represent the first order transfer function. Any question? So based on this, we can substitute the value. So here already we have the K equal to 1. Tau equal to rho V divided by W. What is the value of the density?
One zero five zero.
1050. Volume 5. Volume
4.
4. Okay. And then the mass flow rate is 500.
Yes.
Alright. So determine the value of the tau.
Eight point four.
8.4. Alright. So for the first order transfer function, for the first transfer function, the K equal to 1 and the tau is equal to 8.4. For the second transfer function, K equal to 1 over WCP. 1 over 5, W is 500. And the CP, what is the value of CP?
5.
5. Okay, so the K will be
4 times 10 power negative 4.
4 times 10 negative 4.
Yes.
Alright. And then the tau is rho V over W. So the tau will remain the same, like the first transfer function, which is 8.4. So basically, in this case, you have different value of the K, and then the same value of your time constant. So the next step is you can substitute back into the equation. T prime S equal to 1 over 8.4 S plus 1. T in prime S plus 1. 4 divided by S plus 1. Q prime S. Alright. So here I already substitute the value of the K and the tau inside my equation. So since this is the first order transfer function, so when I have the first order, if you try to refer back page 61, equation 417. Ys equal to Km S tau S plus 1. So you can have 4.18. Yt equal to Km 1 minus exponent negative t over tau. Alright. So whenever I have the first order transfer function, then it's automatically, this is my inverse Laplace. Only here I need to determine what is my m over s here. So here the inlet temperature, based on the statement, if the inlet temperature is changed to 100. So originally, based on the earlier statement, this is my Ti and this is my T bar. Ti bar 150 and T bar 200. So Ti bar, oops. So here my Ti bar is 150 and T bar is 100. Oh, 200, sorry. All right, and then the question, inlet temperature is changed to 100. Inlet temperature is changed to 100. Inlet temperature, Ti, is changed to 100. Okay, so this one is changing. And then the second statement, heat duty is changed to 300. Heat duty is changed to 300. So my Q bar to Q change to 300 kilojoule per hour. So based on this, I need to know what is my Q bar because they must be changed. For example, the inlet temperature initially is 150. It has been changed to 100. For the Q, it has been changed to 300. So what is my Q bar? Q bar can be obtained from the answer of question 1B. Question 1B, this is my Q bar. 125,000. 125,000. 125,000. All right. So when I have this value, then I can determine the magnitude. So the T inlet here, the T in prime is my magnitude. Let's say I put M1 lah. So T in prime is equal to 100 minus 150. Negative 50. And then the Q prime. The magnitude for the Q, let's say I put M2 equal to 300 minus 125,000. Or this one, sometimes we call it Q minus Q bar. So to get the Q prime. The difference between the dynamic and steady state also represent my magnitude. So 300 minus 125,000 become negative 124,700. So this is my magnitude number 2. So here I already have the magnitude. So I know that this one is based on the first order. So what happened next is to translate it into time domain. So this is my Laplace. So if I translate it, I did the inverse Laplace. Then this become T prime T equal to, since this is the first order, I can put K M 1 minus exponent negative T over tau. Since I have two transfer function, I can put K1 M1 tau 1 here, just to differentiate. Plus K2 M2 1 minus exponent negative T over tau 2. So this, the first part represent this one. And second part is this one. So I can substitute the value. For since the first transfer function relating to the inlet temperature. So inlet temperature, this is my negative 50 is my magnitude. So here I can put it back T prime T. K1 is 1. M1, since this one based on the inlet temperature, it becomes negative 50. 1 minus exponent negative T over tau 1. Tau 1 is 8.4. Plus K2. K2 is 4 times 10 negative 4. And then the M2. M2 here based on the Q magnitude, which is negative 124,700. Multiply with the 1 minus exponent negative T over 8.4. Alright. So, since we already achieved the first order transfer function, then we can simply take the inverse Laplace form. Based on the inverse Laplace form, we substitute all the parameter inside the time domain response. So for this case, we already substitute it. Now the only problem here, we don't know the value of T. What is the value of T? So if we take a look, the time is not given. It just mentioned what is the outlet temperature at new steady state. We already substitute the inlet temperature magnitude and the heat duty. When it's referred to the new steady state, if the time is not given, then we assume new steady state value occur at T equal to infinity. This is the standard rule, standard guideline. If the time is not given, then we can simply assume time equal to infinity as our new steady state value. So please take notes that. So meaning that in this equation, we know that T prime is T minus T bar equal to here negative 50, 1 minus exponent negative infinity divided by 8.4 plus 4 times negative 4 multiply with negative 124,700 is negative 49.88. 1 exponent negative infinity divided by 8.4. So T minus T bar, T minus 200. So the T bar here is 200. So what is the answer for the right hand side? Is negative 99.88. So here the answer should be 100.12. So this is supposed to be the answer. So do you know why exponent infinity becomes 0?
Yes.
Alright, okay. So this is supposed to be the solution. Please check your answer if your answer is in accordance to me or not. So any question? Khairul Nizam?
No, doctor.
Okay, dapat jawapan.
Dapat.
Nishanti.
No question, doctor.
Okay. Amir Sharifuddin?
Yes, doctor.
Any question?
So far, no. Just need to digest.
Okay. So in this case, I already provide the solution. I will share this solution in our Google Classroom. Please take a look later. On this Wednesday, we will take a look another example on how the question can be solved for familiarization to all of you. So we already reached the end of our class today. It's almost 2 o'clock. So I think that if there is no further question, then we end our class for today, and I see you online again on Wednesday. With that, thank you very much for your attention.
Thank you,
Alright,
doctor.
Thank you.
Doctor, the test
Okay.
is on
Yeah.
15th, right?
What? Test on 15, yeah.
Alright. Covers 2 chapter, 8 to 10 p.m., right?
8 to 10 p.m. Yep.
All right. Thank you, Doctor.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.